is Alexia Ulol, and today I'm going to present to you Lab 5 Magnetic Bracking with Faraday from Physics 2212. For the purpose of the lab was to collect data of a bar magnet falling through an aluminum foil tube and compare this data with a computational model. With this data, we will be able to apply Faraday's law. The physics principles present on this lab are Faraday's law, as you can see here, the Biot-Savart law to calculate the magnetic field of a bar magnet, Ohm's law, as you can see here, magnetic flux, and Newton's second and third law. For the preview of results, the average time measured of the falling bar magnet was 1.214 seconds, and the average time measured by the computational model was 1.167 seconds. For the experiment overview, first, using the magnetometer app, identify which end of the bar magnet is pointing north. Holding the aluminum foil tube vertically, insert the bar magnet inside of the top end and record with a smartphone timer the time it takes for the bar magnet to reach the other end of the tube. I recorded the time it took for the bar magnet to reach the other end 5 times and recorded the average time. Here, this is a diagram as to what the experiment might look like, and the system is the bar magnet and the tube, and the surroundings were Earth. Here is the data and some assumptions, such as air resistance is negligible and the only forces acting on the system, the bar magnet, are the gravitational and magnetic force. Here are some of the data points collected, and as you can see here, these are the different trials and the time that was calculated, and finally the average time from the results. Here is the glow script code for the lab. At first, here you can see the different constants that were used, and all of the measurements from the aluminum foil were also used in the code. The magnetic dipole moment from lab 3 was 2.042. However, for this lab, it had to be changed to 4.6 in order for the measurements to be more accurate. In this part of the code, the magnetic field of the bar magnet was calculated using Biot-Savart's law. Also, the derivative of the flux, meaning the EMF, have to be calculated. In the last part of the lab, the gravitational and magnetic force on the bar magnet were used on the code. To calculate the net force, the gravitational and magnetic force had to be added together. Finally, using Newton's second law, we were able to calculate the magnet's velocity and position. These are the results obtained from the computational model. As you can see, using the magnetic dipole from lab 3 would have changed the results significantly. When doing the experiment, the average time did not match up with the computational model using the magnetic dipole moment of 2.042. So I changed it to be 4.6 after several trials using different magnetic dipole moments. For interpreting the simulation, the intensity of the coloring of the tube indicates the magnitude of current flowing through each of the ring. Red and blue indicate current flowing in opposite directions. So the red color represents the counterclockwise current, and the blue color represents the clockwise current. This was determined using Lenz's law. What happens to the dynamics of the system when you flip the magnet around? If the magnet were to be flipped, not much would change in the results. The only thing that would be different would be the direction of the induced current on the tube. How does the total time in tube of your real-world system compare to that of the computational system? The times were very similar, and to make the model more accurate, the magnetic dipole moment would be calculated again, since we can see that causes a significant change in results. The shape of the velocity versus time graph shows that the forces at first are not balanced, since we see a change in velocity, and when the magnet reaches the middle section of the tube, it seems as if the forces are now balanced, since the velocity is not changing drastically. Finally, at the end, the forces are also unbalanced. For the what-if part of the experiment of the lab, the resistivity of the conductor. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The induced current on the aluminum tube would increase, meaning that the magnetic force on the bar magnet would also increase. Since the magnetic force would be greater than the gravitational force, this might keep the bar magnet from falling down the tube. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The opposite to the prior question would happen. The induced current would decrease, hence decreasing the magnetic force. The gravitational force would be greater than the magnetic force, making the magnet fall faster through the tube. Thank you.